Okay, today we are going to talk about this compressibility factor. So this ideal gas equation, EGR3, is only valid when the density of gas is low, so which means when temperature is high or pressure is low, then you can use this ideal gas equation. What if we don't meet these conditions? Then we can use this compressibility factor Z to modify this ideal gas equation. So instead of PVRT, we can say PV is ZRT, and this Z is the compressibility factor, and we can find this Z by using this compressibility chart. Okay, so we are going to learn how to use this compressibility chart to use this modified ideal gas equation. Then let's see how we can use this compressibility chart. If you look at this horizontal axis, you can see this one is reduced pressure, PR. This PR can be determined by this equation. PR is the pressure of a system divided by critical pressure. And each line represents a specific T of R, reduced temperature. That can be determined by this equation. The temperature of a system divided by critical temperature. Then, where can we find this critical pressure and critical temperature? We can go to table A1. We can go to table A1 to determine critical pressure and critical temperature. If we go to table A1, this one is critical temperature and critical pressure. So you can find these values for different gases, okay? So that's everything about how to use this compressibility factor. So let's solve this problem together to learn how to use this compressibility chart. So we want to determine the specific volume of superheated vapor at 16 megapascal and 360 degrees Celsius using the ideal gas equation and the compressibility chart, and finally with the steam table. Of course, the exact answer is going to be this steam table. Then we are going to see how much error we get if we use this ideal gas equation and how much error we can reduce by using this compressibility chart. But if you have superheated water vapor, then a correct answer can be found by this steam table. Okay, so let's do that. We are going to use this ideal gas equation first. The ideal gas equation is PV is RT. Then the pressure of the system is 16 megapascal. I'm going to use kilopascal, so that's going to be 16,000 kilopascal, because I don't want to do a unit conversion. in this equation. And gas constant R is going to be, can be found from this table A1. The molecular weight of water is going to be 18.02. And if you know this molecular weight, you can determine the gas constant. This gas constant can be determined by this equation: universal gas constant R bar divided by molecular weight. And this universal gas constant is always 8.314 kilojoule per kilogram, kilomole Kelvin. And the molecular weight can be found from this table A1. For water, it is 18.02. 18.02 kilogram per kilomole. So we can cross kilomole out. So the gas constant has a unit, kilojoule per kilogram Kelvin. And the temperature of the system is 360 degrees Celsius. So if I write 360 degrees Celsius, we can determine the specific volume. Is that right? Right. It needs to be in Kelvin. You remember there was 7 stars, right? Now I need to add 1 more stars. So the star times to the power 8. So 360 plus 273 is going to be the temperature that you are going to use. Kelvin. So if you solve this equation, you get the specific volume. Let me do that. So 8.314 divided by 18.02 times 360 plus 273 divided by 16,000. 0.0183. 0.0183 cubic meters per kilogram. This is incorrect because we cannot use the ideal gas equation for water. But we just used it just to show how much error we get if we use ideal gas equation for water. So this one is, this one must have a lot of error. So let's reduce that error by using compressibility chart. So how can we use compressibility chart? We need to know 2 properties, P of R and P of R. Reduce the temperature and reduce the pressure. So how can you determine reduce the temperature and reduce the pressure? We can use this equation. For reduced temperature, P of R can be determined by the temperature of the system divided by the critical temperature. Reduced pressure, P of R, can be determined by the pressure of the system divided by the critical pressure. So what is the temperature of the system? 360. So 360. And what is the critical temperature? Where can we find from here? The critical temperature of water is 647.3. 647.3. So if you solve this equation, you get P of R? No. Why not? Because we have to use Kelvin. So start to the 9. So 360 plus 273. That's how you get reduced temperature. What is it? 360 plus 273 divided by 647, we get 0.98. So this one is 0.98, close to 1. What about reduced pressure? T, the pressure of the system, which is 16 megapascal. So 16 megapascal divided by its critical pressure of water can be found from here, 220.9. And let's look at the unit. It is bar. So 1 bar is 100 kilopascal. In other words, 1 bar is 0.1 megapascal. So 220.9 is going to be 22.009 megapascal. So if you calculate reduced pressure, T of R is going to be 16 divided by 22.09, we get 0.72. 0.72. So once you get T of R and T of R, you can go to this compressibility chart and find Z, the right-hand side, and I mean the vertical axis. So T of R first, 0.98. So this line represents T of R of 2, 1.5, 1.3, and 1.2, 1.1, and 1. So 0.98 is going to be slightly, the below this line, okay? And what about T of R, 0.72? So this horizontal axis is P of R. So where is 0.72? Around here. So let's find Z value. Slightly lower than that. So approximately here. Then this is where Z value is. 0.67? Okay. So 0.67. So now let's use the modified ideal gas equation to determine the specific volume of water with Z value of 0.67. So what is the compressibility? What is the modified ideal gas equation? PV is ZRT. So here pressure is 16 megapascal, so 16,000 kilopascal. Z value is 0.67. Gas constant R can be determined by this equation, 8.314 divided by 18.02. And the temperature of the system is 360. So I'm going to write 360 again. You don't do that, right? Not to the 10th. So 360 plus 273. Then if you solve this equation, you get the specific volume. So let me do that. 0.0183 times 0.67. I get 0.012. So if you do if you calculate the specific volume by using the compressibility chart, we get 0.012 cubic meters per kilogram. And if we use this ideal gas equation, it was 0.018 cubic meters per kilogram. Now let's determine the exact value by using the steam table at 16 megapascal and 360 degrees Celsius. Where is it? 16 megapascal, 360 degrees Celsius. The specific volume should be 0.01105. 0.01105 cubic meters per kilogram. So this one is from the steam table. This one is from the compressibility factor Z. PV is ZRT. This one is from the ideal gas equation. PV is RT. So let's calculate the error between these two and between these two. So the first one, 0.0183 minus 0.01105 divided by 0.01105. The error is 66%. So how do you determine this error? 0.0183 minus the reference value, this one, 0.01105 divided by 0.01105. Then the error is going to be 0.656, approximately 65.6%. So do you accept this error? No, that's too much, right? That's why we cannot use the ideal gas equation for water. What about if we use the compressibility chart? What is the error? 0.012 minus 0.01105 divided by 0.01105. We get 0.086. 0.086, which means 8.6% error, which is much less than this error, however, still quite significant error. So you don't want to use the ideal gas equation or the modified ideal gas equation for water system. Whenever you have water, please use this steam table, okay? Any question about this problem? Compressibility chart. It won't be in your first exam. You know that, right? No question? Then let's move on. The next part of chapter 3 is moving boundary work, which is very important. So from chapter 2, we studied the ideal gas equation. I'm not that the ideal gas equation, the general energy balance equation. The energy balance equation for a closed system is going to be Q in, W in, minus Q out, minus W out is going to be mass times U2 minus U2 plus, which is the internal energy plus kinetic energy, velocities to square divided by 2 plus specific potential energy, gravity times elevation Z, minus mass times the total energy at the initial state, U1 plus kinetic energy square and plus potential energy. We usually neglect kinetic energy change, potential energy change when we have a closed system. So the general energy balance equation is going to be Q in plus W in minus Q out minus W out is going to be mass times U2 minus U1, the difference in the specific internal energy. So this is the general energy balance equation. The left-hand side shows energy transfer either by heat or work. Okay, so it's going to be energy transfer. The energy is provided in the form of heat or work. And after this energy transfer, because of this energy transfer, there is change in the energy of a system. So this is the change of energy of a system. So when the total energy of a system changes due to this heat and energy transfer, let's say temperature of the system goes up or internal energy changes. So whenever there is change in the system, we write on the right-hand side, we write them on the right-hand side of this energy balance equation. Then there is one problem, which is this is a rigid container. So that means that volume is constant. V1 is the same as V2. And what about if we have this piston cylinder device? The difference between a rigid container and piston cylinder device is its volume can change. If you heat this rigid container, so if you heat air in the rigid container, then its temperature goes up. Let's say from 20 degrees Celsius, from room temperature, it can go up to 90 degrees Celsius, no problem. So if we heat the system, Q in, what if we heat this piston cylinder device? So there is air inside at 20 degrees Celsius. So the initial energy of this air in this rigid container and the air in this piston cylinder device, they are equal, right? Because they are at the same temperature, same kinetic energy, same potential energy, and same phase. So there's no difference in the total energy between this air and this air, right? Now we are going to heat the system by providing this Q in. So this is the rigid container, the air in the rigid container. And if you heat this piston cylinder device, what's going to happen is there is an expansion. If you heat air, the air expands, right? So there's air, and the final temperature is 90, the same as this one, 90 degrees Celsius, but it occupies this much volume. Now, can you say the total energy of the air in this rigid container is the same as the total energy of the air in this piston cylinder device? They don't look the same, right? This one should have more internal energy because it has much larger volume, right? If you increase the volume, that means that you need to provide work. So, the work is done on the system. So the air in this piston cylinder device has more energy than this one. But if you look at this energy balance equation on top, this U1 represents the internal energy for 20 degrees Celsius, and this U2 represents the internal energy for this 90 degrees Celsius, and it is a closed system, so mass is the same. So by using this equation, how can you distinguish the difference in the total energy between here and there? We can, right? Because then why there is a difference in the total energy? Because there is more work because of this air expansion. So piston was here, and this air pushes this piston upward. So more work is done on the system. So the total energy of the system here should be greater than the total energy here. But this energy balance equation cannot explain the difference. So we need to add one more, the term on the right-hand side. That is moving boundary work. So there's a work is needed to move this piston from here to there. So we need to increase the thermal energy because there's a temperature increase from 20 to 90. Okay, I get that. And there's the same amount of internal energy change from 20 degrees Celsius to 90 degrees Celsius, but there is additional work, which is the expansion of this air. So can you determine this air? How do you determine this air? How much, how much work is given to the air to move this piston from this original location to this, the new location? How much work should be given? I told you this when we studied chapter 2. How much work is needed to move that, the piston? Think about mechanical energy. So we are, pushing this piston. So this object, this piston is moving. That means that work is given. What kind of work? Electric work? No. What the object is moving, that means mechanical work. So what kind of mechanical energy did we study in chapter 2? Kinetic energy, potential energy, and what is the last one? The U is internal energy. So there were three in mechanical energy in chapter 2. Kinetic energy and potential energy, and there was one more mechanical energy which was not part of total energy. What was it? Flow energy. Pressure times volume. Do you remember that story that this room is completely filled with the students when someone wants to walk in? What this, the new mass need to do? It need to push it, whatever the mass in front of the door and then make the space. Then, the mass can come in, right? The same thing. If you want to move this piston upward, you need to provide pressure on this piston, right? If you provide pressure on the piston, so this is the pressure of the air. And if we assume that there is atmospheric pressure on top, PATM, if the pressure by air is greater than the atmospheric pressure, then this piston moves upward, right? So that pressure, but how high? By this much volume, So how much work is needed? This pressure times this much volume. So pressure times volume is the energy required, is the work required to move this piston from this location to this location. That is here. But we don't know whether pressure is constant or variable. So we cannot just say pressure times volume. You can say pressure times volume when pressure is constant. But pressure can change. So to account for that, it's going to be integral of pressure over volume from 1 to 2. So this is the work required to move this piston from this location to this location. That is WB. What this B stands for? Boundary. That is moving boundary work. Then where this moving boundary work is from? This is the work done by the air to the surroundings, because this air is pushing the piston away, right? So this one is doing work to the outside. So when you talk about the direction of energy transfer, it is going to be W out. So this WB, the moving boundary work, because this is the work done by the air to the outside, so that should be a part of W out. Then this equation should be rewritten as Q in plus W in minus Q out. Now this time minus WB, moving boundary work done by the system to the surroundings, because the system is pushing the piston away, right? And this might not be the only energy transfer by work. This may not be the only W out. So we may have another W out. So W out everything but moving boundary work, B, is mass times U2 minus U1. And then once this WB is done by the air to the surroundings, is it going to be gone? Now, because of this, there is an expansion of air. So the total energy of the air is going to increase by the same amount of this WB, right? So this WB, even though this is work, it's going to be a part of total energy at the end. Am I right? Because after the expansion, it doesn't go back, right? It stays there. So the volume of this air is increased and it stays there. So the work is given, this much work is given by the air is going to be a part of total energy at the end. So to be correct, this is going to be the part of total energy should be on the right-hand side, right? Because in the energy balance equation, these are energy transfer, and this is the change of energy. Even though this is the work done by the system, this moving boundary work, it's going to be a part of energy of the system. So it's going to be the change of energy of a system, so should be on the right-hand side. Then this equation should be rewritten as Q in plus W in minus Q out minus, this one goes to the outside, W out but moving boundary work is mass times U2 minus U1 plus WB, and this one looks too ugly, so let's just get rid of it. Then this is the energy balance equation for a closed system. So this is the energy balance equation you are going to use for closed system. The final version. Then what we need to do, once we know that this is the final version, how do we know, how do we calculate, how do we determine this Q? When we go to EGR356 heat transfer. So you can determine this one next year with me. Not with me if we register, the EGR356 next semester, because I will be gone for sabbatical. I will be back in the fall anyway. Then what about this W? How do you determine that? We already studied how to determine this W in chapter 2, right? Like electric work, it's going to be voltage times current times time. And what about this mass? Or it's a closed system. And what about U2 minus U1? We studied how to determine U2 minus U1. You remember the table problem, right? Now, if we have water or refrigerant, we can make a property diagram and determine the phase change process and evaluate this U1 and U2, no problem. What about this WB? Do you know how to determine this one? Not yet. So we are going to study how to determine this WB. Then we can use this equation. That will be all for chapter 3. So we have two more sections. One is how to determine this WB. And once we learn how to determine WB, then let's apply this energy balance equation everywhere whenever there is a closed system. So that's the plan. These are how to determine WB. Moving boundary work. So so the way we determine moving boundary work is simple. We can just solve this equation. WB, moving boundary work, can be determined by integral of P over volume from the initial state to the final state. So if you solve it, you get moving boundary work. Simple, right? You like that? You don't like that, right? Don't worry about that. Those genius in the Pierce Hall, who are they? Those majoring mathematics already solved this one for us. So let's see what they found. So solving this WB in general can be complicated because pressure can change, volume can change. So it is convenient to think about a special process. So let's talk about the simplest one first, constant volume process. So if we have a constant volume process, what is moving boundary work? Anybody can answer that? If we have a constant volume process, what is the moving boundary work? Right, it's a constant volume, so there's no volume expansion, there's no volume compression, so there's no moving boundary work. WB is 0. The second thing, constant pressure process, constant pressure. Oh, if it is constant pressure, We can solve this one, right? Let's talk about mathematics a little bit. It's not that hard. If it is constant volume, what happened to this P? It's constant. I just said it's a constant pressure process. If this P constant, what do? If there's a constant inside the integration, what do you take it out, right? So go out. Then we have P times dV from 1 to 2. Can you solve this one? V2 minus V1, right? There's nothing inside. So it's going to be V2 minus V1. First time to see? No. If you solve this one, it's X2 minus X1, right? So this is P times V2 minus V1. In this equation, V1 means the initial volume, V2 means the final volume. Then is this P P1 or P2? So V1 is the initial volume, V2 is the final volume. Should this P P1 or P2? Yeah, they're the same. So if you see there's no subscript, means that you can put either P1 or P2 because they are the same. So if you see nothing here, you can put anything, 1, 2, 3, 4, 5, 6, 2000. As long as it is a constant pressure process. And then the third one, now it's going to be complicated a little bit, very little bit, okay? So constant temperature process. Now let's solve this equation. WB is integral P over volume from 1 to 2. Can you solve this one? For now, we can't. Why? Because we have no idea about this P. We have no idea how this P is related to this V. So you cannot solve this equation. So what do you want to do? We need to find the relation between P and V. Is there any equation that you studied in chapter 3 that shows the relation between P and V? In other words, did you remember any equation that we studied in chapter 3 that has P and V together? Yes, what is it? Yes, the ideal gas equation. So let's talk about the ideal gas equation. I need a scratch paper. I put like, the 20 of them here in this drawer. Somebody took it. My precious 20 scratch papers, somebody took it. Okay, so I'm going to use this one. So let's talk about PV. Wait, I can write it here. No, here. PV is nRT. So if you look at this equation, this P is a variable. Yeah, I know it's a P is a variable. Can be any number, 100 kilopascal, 200 kilopascal. When there's a rain, what happened to the atmospheric pressure? Goes down a little bit, right? When the sunny day, it goes up a little bit. The pressure can change. It's a variable. Oh, I said constant. That's wrong. So variable. What about this volume? It's variable. If the air occupies this classroom, that means that the volume of the air is this classroom. If you go to the next classroom, there's an air, and the volume of that air is going to be different from the volume here. So the volume of air is variable, can be any number. What about mass? We're talking about a closed system. So what is the definition of a closed system? Something closed? No, the definition of closed system is that the mass does not change. So mass does not change. So it is a constant. It is not variable. So now there is a constant. What about gas constant? Is the gas constant a variable or constant? That's too silly, right? The name is constant, so it's a constant. How do you determine that? The universal gas constant R bar divided by molecular weight. So universal gas constant is always 8.314 kilojoule per kilomole Kelvin, and the molecular weight can be found from table A1, right? What about temperature? Is a variable or a constant? Everyone talks about active learning these days, so I kind of need your responses, right? So it's constant or variable? Right, because it's a constant temperature process. So that is constant. That means everything on the right-hand side is constant. So what is the relation between P and V? There's a relation. P times V should be constant. Then we can say P is constant divided by volume. Okay. Then can we put this one here? Yes. This is some constant dV over V from 1 to 2. So how can you solve this integration? There's a constant, there's a C inside. What happened to him? When there's a constant, you kick it out, right? So this C comes out. So this equation becomes C integral from 1 to 2 dV over V. Do you know how to solve this one? Integral dx over x. What is the solution for that? Yes, ln x, natural log. So this time, this is going to be natural log of V. So this is C times natural log V from 1 to 2. So how do you solve this one? C times natural log V2 minus natural log V1. So if we have natural log A minus natural log B, how do you simplify it? So natural log A minus natural log B is going to be natural log A over B. Am I right? If you don't remember, I just wrote them here. So now you remember, right? So then WB becomes this C times natural log V2 over V1. Is that it? Now, this C is unknown. So what is this C? This C is pressure times volume. C is pressure times volume. So I can write this one is WB is pressure times volume natural log V2 over V1. Then you can see, you can find this one again. Oh, there's no subscript here. So is it P1 V1 or P2 V2? Doesn't matter because I just said PV is constant. So this constant can be P1 V1 or P2 V2 or P3 V3 or P2 2 million, V2 million. No problem, right? So that's constant temperature process. If you have a constant temperature process, this is how you determine moving boundary work. PV natural log V2 over V1. You can say P1 V1, P2 V2, it doesn't matter. But you cannot say P1 V2 or P2 V1, right? If you use P1, this V should be V1, okay? And how did we get that? by using this relation. dV is constant. So these are three very unique processes: constant volume, constant pressure, constant temperature. What about if you have a gas and the process doesn't belong any of them? Then it is called polytropic process. This is how real gas behaves. And our assumption is that dV to the power n is constant. That's a real gas behavior. dV to the power n is constant, polytropic process. Number 4, polytropic process. PV to the power n is constant. Now let's determine WB. WB is integral from 1 to 2 P dV. So can you solve it? We can't, because we don't know the relation. Oh, there is a relation. So let's move this V n to the right hand side. How can you do that? Divide by V to the power n. V to the power n. Then you can cross them out. This P becomes some constant divided by V to the power n. Or you can say V to the power minus n. That's the same thing, right? And now this one is going to replace this P inside. So it's going to be from 1 to 2, some constant times V to the power minus n dV. And can you solve it? Yes, we can. This C comes out first. Some C So if you have integral x to the power n, dx is going to be n plus 1, 1 over n plus 1, x to the power n plus 1, okay? So this one becomes, instead of n, we have a minus n. So it's going to be minus n plus 1. In other words, we have a c in front, c over minus 1 plus 1. No, 1 minus n, same thing. V to the power minus n plus 1, 1 minus n. Then what is this C? C is dV to the power n. So this C is dV to the power n. So this WB becomes PV to the power n. By the way, this one is from 1 to 2 over 1 minus n V2 1 minus n minus V1 to the power 1 minus n. Then this PV can be P1 V1 to the power n or P2 V2 to the power n. So if you multiply this one with V2 to the power 1 minus n, it's going to be P2 V2 P1 V1 to the power n times V1 to the power 1 minus n minus P1 V1 over 1 minus n. So we got this equation by using this relation. PV to the power n is constant. So that's how you determine the moving boundary work in a polytropic process. This n is polytropic exponent. Where do we get this n? From a table? No, from an experiment. So this n is going to be case by case. So that's real gas behavior. So 1, 2, 3, 4. Then let's find one more way to determine this moving boundary work. I'm pretty sure that you didn't like this mathematics. So let's use a graph. So now we have a graph. How do you determine this WB PDV on a graph? If you make pressure volume diagram, PV diagram, if there's a initial state number 1, if there is a final state number 2, I don't know how they are connected, maybe like that. The area is going to be moving boundary work. But there's one thing we need to be careful. This moving boundary work is positive when it is an expansion process. This moving boundary work is negative when it is a compression process. So that's the whole theory about moving boundary work. Any question? So we have 15 minutes. We can solve 1, 2, 3. Oh no, just 2. Let's solve one problem, and then we can talk about the exam. Calculate the total work in kilojoule produced by the isothermal process of the figure when the system consists of 3 kilograms of oxygen. So we want to determine the total work produced by this process unless there is an additional external work. This work is going to be moving boundary work. And it is an isothermal process, which means temperature is constant. When temperature is constant, what is the the moving boundary work equation? This one. So let me write that equation here. WB is PV natural log V2 over V1. How did we get this equation? By using this relation. PV is constant. Okay. Now we can try to solve this problem. So if you want to use this equation, let's see what information we get. So this one is the initial state. At the initial state, what do we know? Pressure 200. P1 is 200 kilopascal. What else? Do we know the volume? Unfortunately, we do not. What about the final state, number 2? The specific volume, V2, is 0.2 cubic meters per kilogram. What about pressure? 600. So P2 is 600 kilopascal. Then, can we solve this equation? We can try. Oh, there's one problem. We don't know V1. And let's determine V1. By how? By using this relation. P1 V1 is P2 V2 is P3 V3 P2 million V2 million. You remember that, right? So we can use this one. What is P1? 200 kilopascal. What is V1? That we don't know. P2, 600 kilopascal. What about V2? 0.2? No, this is the specific volume. This is the actual volume. We know the mass of the system. So if you want to determine V2, this V2 is going to be mass times specific volume V2. This mass is 3 kilograms, and this V2 is 0.2 cubic meters per kilogram. So the actual volume at the final state is going to be 0.6 cubic meters. Then, can you determine V1? Yes, we can. If you solve this equation, we get V1 that is 1.8 cubic meters. Then, in this equation, this is 1.8. This is 0.6. This one, we can say P1, V1, or P2, V2, doesn't matter. I'm going to say P1, V1. So V1 is 1.8. P1 is 200. Can you determine WB? Yes. If you do, you get minus 395.5 kilojoule. Why there is a negative sign? On the system. So that means that it's a compression process. If you look at the volume, the initial volume and the final volume, so you can see it's a compression process. The work is done by the surroundings on the system. So that's how you determine a moving boundary work. We have one more problem. This one, but looks pretty complicated. So let's do it next time. We have 10 minutes. Let's talk about the exam. You should be very happy about the first exam because you already know what are the problems in the first exam, right? So the exam 1 has 4 problems, 1 hour,